It's 8 o'clock. Welcome all. And we will start our Starry Starry Night session 9. And today we again have a strong lineup. We have Ivan, we have Chris, we have Yannick, we have David, we have Alex, and we have James. And again, we plan to talk about 4 questions today, right? And we will show us the first question is a counting problem. And Ivan is going to show us. And we will give our students about 3 minutes to try to solve it. And we will see how many of them have the correct answer and how many of them have the wrong answer. Find the number of arrangements of 5 red balls and 11 blue balls in a 4x4 table so that each row and each column contains at least 1 red and 1 blue ball. See, they learned James' great counting problem. Let's see how our students do this one, right?
Exactly.
So let our students try for 2 minutes, and Ivan can show a poll.
Yes. While they're trying, I can say a few words. How did it end up to be made? We usually have summer and winter camps at IDMF. So for the winter camp, we prepare some problems from the past competitions. And some of them we change, and we change not only numbers. Sometimes if we don't like the problem, we change the whole problem. So there was a problem, very similar, 4x4 grid. I don't remember from which competition. And I thought it was kind of non-interesting. And I changed it to this one. So I put 5 balls, 11, and I just left it. And I think a few days before we were to use this problem in class, one of the teachers, Mr. Luyan Wong, approached me, and we disagreed about the answer to this problem.
And by that time, you know the question is quite hard.
How can you disagree about the answer?
Yeah.
There's only 16 choose 5 cases.
Oh no.
Yeah, so, and after we gave it in class, where there were very interesting ideas about this problem, and at the end we agreed it would be a very cool AB problem to test students. Okay, we can talk about the first step.
No, you want to show us the poll? Let the students show us what their answer is, right?
Okay, let me launch the poll.
Well,
I'll keep it
choice
open.
Now.
Do you guys see the poll?
Okay, I got one of those answers. It's good. Means I have at least a 1 in 5 chance of being correct.
Now this is an AMC problem.
That's not how math works.
The people who made the multiple choice questions, they've done their job.
Isn't it always like C or something?
Yeah, they have to be in increasing order.
I don't actually know what the answer is to this question, so, but it's always C.
These are all multiples of 72.
I just made it. Sorry, I had to make it somehow.
Aren't you supposed to design it so that if people can guess that it's supposed to be divisible by 72, they're supposed to be like rewarded with like a 25% chance to 20% chance or something?
Okay, people are voting. I can talk about one thing. We have 5 red balls and 11 blue balls, and we have so many blue balls, it looks like they don't matter. So we need to persuade ourselves that indeed they don't matter. In what sense? If we have a condition that fails for blue balls, then it also must fail for the red balls. Let's check. If we have a row, let's say, that doesn't contain blue balls, right? Sorry. So no blue balls. It means we must use here all 4 red balls, right? Which means it will not be satisfied for red balls at the same time, because you will have at least one other row without a red ball, right? So what I want to say, you just don't care about 11 blue balls. You just solve the problem with about 5 red balls. You place them into 4x4 grid, so it contains at least one red ball in each row and column. I hope that makes sense, right? So should we stop the poll?
Yeah.
Okay, so 2.5 minutes passed. Let's see. Do you guys see the results? We have 10 people think it's 288, 4 people that is 144, and 212, it's for 216, 360, and 432. Are they distinguishable? An answer, a question from the audience. All the
balls of the same color are indistinguishable.
Yeah.
And we cannot
That's a good-
rotate the board, right? Yeah, the board is a board. We already placed it there.
Yeah. If there's
That's a good-
distinguishable, then the answer should be like sum total of 11 factorial and stuff, which you can infer actually from this formula.
Yes, the balls are indistinguishable. So what is a common approach to this problem? We have 5 red balls, right? So, and we need to occupy each row and each column. So let's place 4 of them in some way, so they don't occupy, so these 4 occupy each row and each column, and then we place the 5th one, right? So place 4 and deal with this condition and add the 5th one.
Yeah.
So how many ways to do that? Maybe some people in the audience can help me with this idea.
4 factorial times 12, someone said.
4 factorial times 12. 4 factorial is the number of ways to satisfy, place these 4, right? So in 4 ways we choose what will be where will be the ball in the first row, 3 ways the ball in the second row, and so on. And in the 5th one, there are 12 places left. So it makes sense. It is how much?
Well, that's 288, but you're not sure that you can't get the same placement twice, right?
Right.
You still have
And-
the overcounting.
And that's why the 288 is the best wrong answer. And it also is the exactly what the students answer, or 10 of them, the most popular one.
It is the most popular one. It is wrong. But wait,
Yeah.
Alex, you're saying we need to check that we don't double count, right? Count
Or
the
do we
same
double count?
configuration. Do we?
There are some of them you double count, right? So Ivan, let's draw a picture to show people if you do this way, and then what happens, right?
Wait, Dominic, do we double count? Do we count any of these configurations twice?
I think you can, if you have 5 balls, you can tell which one is the 5th one.
If you have the 5th ball, how do you tell there is exactly 1 row and 1 column with 2 of them, right? And you take the intersection and you know which one is the 5th, so we do not overcount.
Okay, so at least you're showing something, right? At least you're showing now the answer is at least 288.
Yes.
So at least you're better than showing nothing. Like before, it's like you're not even sure if the answer is less than or more than 288.
So there are cases that are not coming from this way.
Yes. And it's not easy to realize, but many students miss such cases. So let's draw one for our viewers. So let's say here, 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 and here, right?
Yeah.
Oh God.
Yeah.
So can you guys see 4 balls that are in different rows or columns? We definitely should choose one, but once we pick any of these 2, we are stuck, right? So there are configurations for which our strategy plays 4th and at the 5th one fails. So now we need to count all of them, okay? So there are many ways to do this one, but I'll use the one that kind of uses symmetry. So let's start counting in the following sense. There is a row with the 2 red balls, right? So first we will choose a dominant row. We will call this row a dominant, right?
Yeah. So this is what I said in other day about making this unsymmetric to stabilize the board, right? Yeah.
Yeah, I learned this method from Mr. Fung because I couldn't solve counting problems at some point. So let's say in 4 ways we can say it is in row number 1, right? So we will multiply by 4. We assume this row is dominant, right? So it has 2 red balls. So we need to choose 2 columns.
Yeah.
Choose 2 columns for these 2 balls, right? For these 2 balls, right? So we can say these are first 2, and we should multiply our answers by 4 choose 2, right? 6 options. So once, and it all goes by symmetry, right? So once we chose these 2, we need to choose what will be the next. And next we can look at the dominant column. And there are 2 options. The dominant column can be one of these 2 or one of these 2, right? You guys agree? Mm-hmm. So which gives us, let's say case 1. Sorry, case 1, it's here. And case 2 will be over here. So in case 1, the dominant 2 columns, the dominant column is somewhere here. So we multiply by 2 to choose which one. Choose dominant column. Right? And the same thing is here. Which one? And then once we choose, if its dominant column is here, let's say number 1, there are 3 ways to position your red ball. So times 3 to position red ball.
Then 2 of them must be in the bottom quarter now, right?
Right. And for here, it's times 2. Let us separate for choose column. And times what? 3 choose 2, because we need which 2 positions will be, let's say, these 2 taken by the red balls, right? So at the end, there are what? 2 left here, as you guys say. You can cross them, or one possibility here.
Can you move the paper up a little bit, Ivan? Yeah, good.
Yeah. Then you add them, right?
So at the end, if you do 4 times 6 times what? 2 times 3 times 2 plus 2 times 3 times 1, you get 432.
Yeah. Okay. So I hope our audience learned something, because at least 10 of them learned how to solve a problem better now, right? So we are exactly on time for the first quarter of the show, and we finished 1 question, right? So we can move on to the next one.
Okay. This is the statement. And
You want to draw the picture?
well, maybe James, do you want to draw? Do you want me to draw the picture?
Yeah, I think it's better for you to draw the picture. Or James, you have a picture.
I guess we're not gonna guess who wrote the problem. I have a whiteboard.
Oh, okay.
Okay, so James, do you want to start or should I draw the picture?
It doesn't matter. They can. I can just share if you're willing to let me share.
Okay.
Okay,
Nice circle. Oh,
almost.
I like to have my circles of radius 5 when I use a grid. It's very helpful. Let's see.
I mean, the circle has radius 12, right? Yeah.
Yeah, but I just instinctively draw radius 5 when there's a little grid. All right, can you guys see my screen?
Yeah.
All right, I'm using a monitor, so I don't. Hopefully it works. Okay. Yeah. So there's a problem. You have a big circle and two smaller circles that are internally tangent to the big circle. You have an internal tangent, so a chord cuts them so that they're on opposite sides of the chord. And then we're given a bunch of random conditions. So this is a problem from this year's HMMT that maybe some of you guys recognize. It was a pretty difficult problem because HMMT individual rounds themselves are already way too hard. And then this is number 7 on a 10 problem test that's way too short of a test in terms of time. So yeah, it's definitely a hard problem, but I think like all the ideas in it are not that difficult. So hopefully it's something that we can go over and kind of be able to understand. So to recap, I drew the diagram on the right. We have a bunch of tangent conditions, and then we have the circle radii, and also some random length condition where x2 t2 is twice the length of x1 t1.
Okay, wait, James, explain the problem. So you have one big circle, one chord, two circles tangent to the chord and to the big circle, right? As shown in your diagram.
Yeah.
And what do you know? You know the 3 radii are 2, 3, and the big one is 12. And you also have points of tangency, x1, x2, t1, t2.
Yeah.
The ratio
one ratio.
Yeah, so that's kind of a random condition. So T1, T2 aren't really utilized, or X1, X2 are like the point of X1, T1, X2, T2 is really just to give you this random condition, right? Otherwise, we just know a bunch of lengths, a bunch of circle radii. And so this gives us the final piece of information to kind of fix the actual configuration of the circles. Because otherwise, we can vary the chord AB and still be able to find circles of length 3 and 2. But this length condition kind of fixes what the chord is. So we should be able to compute what the chord length is here. Does that kind of make sense?
Yeah.
All right. So I'll ask the other panelists. So what is the first thing you do when you see something like this?
Archimedes lemma.
I don't know what that
X1
is.
ty and x2 t2.
Extend x, extend them.
Yeah. I don't know what an Archimedes lemma is, but crap, that's not what I wanted to do. Oh, now everything's misaligned. Sorry.
Undo.
Oh, undo.
Yeah, people are asking what Archimedes lemma is.
Right? Go to the bottom point of the circle.
This is going to be a trip. All right, sounds good.
And that's something our students want to explore, right? They go to the midpoint.
Yeah. So this is so these are the midpoints of the arcs. And the reason why is because it's something called homophoty. So the reason why is from the let's take like x2 for example. Which one's the pointer? There's the pointer. X2.
Why don't you also connect the T and that center, T2 and the center 1, and then O2 and M? Then people can see the homosity very clearly, right?
Okay, sure. Yeah, sure. You're talking about okay. Here. This?
Yeah, and also you draw the perpendiculars. The center to the midpoints.
Center to the mid.
No. From O to M2, and then from the other center to T2. Then they can see this so-called homosity very well.
O to M2, and what is the other thing?
And then from the center of the second.
Okay, this one.
Yeah, there you can see.
Yeah. So basically, you want to look from the perspective of x2. So x2 is a homophoty that takes this smaller circle omega 2 to the big circle gamma. basically if you dilate with a certain factor, you can get from omega 2 to the big circle. And actually, you know what the factor is. The factor is a factor of 4 because it's just the ratio of the radii, which is 3 to 12.
Yeah.
So that means if you go from x, if you dilate out T2 to a factor of 4, you'll get a point on the circle here.
Mm-hmm.
And furthermore, because T2 is a tangency point AB here, that means the AB itself, after the homophily, is going to map to the tangency over here. I need a pen. All right. It's going to map to this tangency over here. Point over here. And then this tangency here is parallel to line AB because AB maps to this line, and homophily preserves like the parallelness of lines, I guess I can say. So in that case, M2 is just going to be the midpoint of arc AB here, the major arc AB in this case. Does that make sense? So we have a midpoint of arc, which is all nice. But we don't really know what to do with that yet. But nice, we have M2. Similarly, we have M1, which is the opposite midpoint of the arc, which is nicer than M1, MO, and M2 are all along the line. That's pretty good. So there's actually a lot more to this configuration that we haven't explored yet. Do you guys know anything else that we can kind of do in this diagram?
Wait, James, was it the diagram you started with to think of this problem?
So this is a pretty standard geometry configuration. I don't really know how to write geometry, so I just started this configuration, played around with it until I could get something that was like not just like trivial applications of things. So like I wanted people to like basically like be able to know like the basic facts of this configuration, and then like it kind of like play with the kind of the lens they could find to be able to solve a problem. So like there's still like one very like standard fact that we haven't explored at all yet. Do people have ideas?
Are you referring to the shooting lemma?
I don't know what that is either. I think I am not. I think so, I think I saw what the shooting lemma was on some HMT solution, but I don't know. No.
Oh yeah, it's that M2A squared is equal to M2T2 times M2X2.
Oh yes, that is what I'm referring to. What are these names?
I don't know where the name shooting lemma comes from. I think it's from 107, but I'm not sure. Yeah, thanks for reminding me that it exists.
All right, cool.
James, you know what you can do?
Yeah.
Can you show that OM2 is perpendicular to that line? Because OM2 is perpendicular to the bottom line because we did this dilation. It was perpendicular to AB. Now it's perpendicular.
Yeah, definitely. They're perpendicular. That's definitely a relevant problem. Part of this problem. So yeah, what David mentions the shooting lemma. M2T2 times. So basically, what he claims is I'll write it here. M2T2 times M2X2
is M2A square, right?
X2 equals M2A squared. And this is like just very simple. It just we can derive it from what we know so far, and that is we know a midpoint of arc. That's basically all we know right now. But midpoint of arc is very nice because it gives us angles, equal angles. So in particular, if we draw this right here, we have some equal angles now. In particular, we have that arc M2A equals arc M2B. So they're going to inscribe the same angles. Inscribed angles are going to have the same measure as well. And in that case, we have that this angle right here, M2AB, angle M2AB. Sorry, this is really hard to write. It's equal to another angle right here, which is angle M2A X2, right? Actually, instead of M2A B, I should replace this, and I'll write it as M2A T2 in this case.
Second one, you want M2 X2A, right? You want to switch.
Oh, yeah, my bad. I'll put I like writing things in counterclockwise order, so I'm going to keep it as I'm going to write AX2 M2. Okay, A x2, m2.
Yeah.
Right? And then this case, we have very nice, we have these two angles are equal. Also, the two triangles share this angle as well. So by similarity, we have that these, actually I can just replace this and I'll just say that these two triangles are similar. I'll just add an extra line in this equality.
Yeah, so this is a very common thing about angle
Now
bisectors,
they're
right?
similar.
Because AX2B have angle bisector X2M2, and this applies to all those angle bisector situations.
Right.
Right.
And then just by simple by simple like length, we have M2 T2 over M2A equals M2A over M2 X2, which is exactly this relation right here.
Yeah.
So we have this, and this is further nice because if you look at this left expression, this is exactly what we call the power of M2 to this small circle right here. So the power is just like I'm gonna assume that you guys are familiar with it, but essentially just like it's a way of expressing like I don't know, like kind of distance away from a circle or something. So it's very useful in Olympiads in terms of proving a lot of cyclic quads or something. Or
James.
Yeah, PowerPoint in general. What's up?
Sorry, can I interrupt for a second?
Yeah, of course.
Look, I explained why M2 and M1 are midpoints of the arcs, right?
Yeah.
So M1, M2 is the diameter, right?
Yeah.
So if you draw M1, X2, if you can draw it, you have a 90-degree angle there, right?
Yeah.
So do you see another cyclic quad that I think helps us to see these things better? Because we have right triangles.
Yeah. So you're talking about M1, X2, T2, and then we'll call this midpoint M or something? Is that what you're referring to?
Sure, yes.
Yeah, so we have another cyclic quadrilateral here, M1, X2, T2, M, which also gives us another, the cyclic quad gives us another PowerPoint configuration as well. This will actually tell us that if you want, it can also tell us that M2, I'll write it down. It'll also tell us that M2, T2 times M2, X2, I'll just add it here. It's also equal to M2, M times M2, M1. So we have a bunch of inequalities here, right? So that's the cyclic quad that Ivan pointed out, which is also true. And this is quite nice as well because we can relate like this random configuration in terms of M2, T2, X2, in terms of like just the diameters and the chord, because we eventually want to be able to find what the length of the chord is. Finding the diameter, or actually finding where M is very useful. Because once we find where M is away from O, we can instantly find the length of the chord, right? Cool. So now we have this these equalities, and we're basically very close to done once we realize what the power of a point is. So now, because this length x2, t2 is 2x, from the homophily, we know that the length x2, m2 as a whole is 4 times that, ratio 12 to 3. So that means that this length over here is 6x. Yeah, and then this length over here is going to be 5x because the ratio of because m1 x1 as a whole is 6x, right? So then we can write the power of m2 to omega 2. We can write this out, and this is just exactly 6x times 8x, right? Which is 48x squared.
Yeah.
And then the power of m1 to omega 1 in this case is 5x times 6x, which is 30x squared.
Yeah.
Okay, we still have this x, but we don't really care about the x. The point that's going to actually minus out. Now we know the ratio of the two powers.
No, I think you are done. I think you just look at the triangle M1, M2, and B. You have two sides already.
M1, M2,
48x squared and 30x squared. They should be 24x squared.
What is 24x squared?
Oh,
M1, M2 is the diameter, right? You are done by that. You look at the big triangle, M1, M2, and B. You know three sides, 30x squared, 48x squared, and the 24 squared.
Yes, that allows you to solve for x.
Oh, I don't actually care what X is.
Okay.
Yeah, you can use the other PowerPoint now.
Oh, I see. I suppose you could solve for X. I did not ever solve for X. I did not realize that we. Okay, yeah.
That's fine. Go ahead. Yeah.
Okay, yeah. So now we can use this equality right here, the M2, this one right here, which is very nice. So we can also compute this ratio another way. This ratio is M2M times M2M1. I'm gonna erase this. This is also equal to M2M times M2M1 over M1 M times M2 M1 M2. And nicely, this thing cancels out right here. So we're left. We know the ratio between M2M and M1M now, right? And in that case, if we know the ratio between M2M and M1M, then we know exactly what these two lengths are, because the total length of the diameter is 24. That means if we know the ratio is 8:5, then we know exactly what these two lengths are, and then that can tell us exactly what the length OM is. For simplicity, I'll just tell you that the length OM right now is 36/13. This is a very simple calculation once you know the ratio of the M1M to MM2. And then that, knowing the radii, that's going to be able to let you calculate AM and then hence AB. You don't need to, I won't go over the exact numbers. It doesn't really matter. But the point is that like we had a lot of really nice ideas here. There was a very nice homosity involved. And then you have the power of a point idea. This is a very standard configuration when you have a circle tangent to a bigger circle and also a chord. And then just finishing off, and the power of a point idea is really nice. I think like knowing that the power of M2x2 times M2t2 equals M2a squared, that's definitely like a standard idea. And then like adding in the rest of these diameters and midpoints and stuff, that's something that isn't necessarily standard. That's something I kind of added to this problem that made it really interesting. So as you can see, like this problem like is really not necessarily that difficult in terms of just ideas, but obviously there were not that many solves during contest, of course, because it is a difficult problem. So I thought it was really nice. So this is the kind of problem that I kind of wanted to write, because I think maybe my very first mop problem back in like 2014 was a problem that like it was I was like green group. I think it was green group, and then our number one on our mop test is a problem that was similar, but it involved like drawing a bunch of tangencies. I think it involved drawing this tangency. So the tangents from M2 to like the small circle, then having these 3 points, and then you have the three incenters of these triangles: A brown point B, AX2B, A other brown point B, and then proving that two angles add up to 90. It's kind of hectic, but like it's just adding even more to this problem. So there's the point is that you could explore even more to this problem. I don't actually know the source of the problem, but I can eventually post the problem that kind of intrigued me. So this is like my very, very first mop test, problem number 1 on my green test. So I like writing problems that like influenced me as a little kiddo. So that's that. Were there any questions?
Yeah, this internal circle tangent and this thing is very, very good. I think it's later on there are IMO problems made based on this. This is a very good thing to know, the structure.
I will also say that 2005 Geo10 from HMT has a very not quite the same configuration, but it does all of these it does sort of the same thing with these these circles and this tangency point. And I think it's one of my favorite Geo problems. Honestly, old vintage HMT G10s are really good. So I actually highly recommend going through some of the old HMT exams, because it strikes a nice balance between good and difficulty.
Yeah, I think definitely the older HMT Geo 10s are at
more
least,
approachable.
10 years ago are definitely like more approachable, less advanced. Geo has definitely gotten more advanced and skyrocketed really fast. Definitely beyond my pay grade, so it's fine.
Keep adding circles, making it more and more complicated.
Yeah, I don't know. Kids these days are very crazy about Geo. I'm glad I've left at the point that I did.
Same.
Yeah, you outgrow it. That's very good. Okay, so we have the next one. Ivan, are you with us? Okay, here we
Yes. Do we launch any polls?
Sure. We need to speed up a little bit here. Let's see. Doesn't matter. If we take long time, we take long time. We can do just 3. So let me read the question, right? Determine what? The smallest positive prime which satisfy congruence p plus p inverse congruent to 25 modulo 143. Wow, 143 is not a prime. That's important.
Yeah, 11 times 13, so we should
Wow.
be careful.
Okay.
Maybe should we explain what's this multiplicative inverse to students?
I think so. Yeah.
Sure.
So because I read it, because I mislead lots of students, I think I got more votes.
Okay.
Okay, we can stop and let David start. It's David's power, right?
Yeah.
The results are over there. Not
Oh,
Chris.
well.
and
Emma still got
That's a
worse.
really even distribution. Wow.
Yeah,
Yeah.
somebody even voted for James. How can that happen? James already had one. Okay, that's okay.
All right. So yeah, let's just briefly go over what multiplicative inverse is. I guess I'll put it on my screen again. Let me get that set up. So the basic idea behind multiplicative inverse is that you can't always it basically acts as the same thing as the multiplicative inverse in the regular case, in the sense that, well, what does the number 1/5 mean? Well, you can think of 1/5 as the number which, when you multiply by 5, you get 1.
David, we can't see much.
Yeah,
now
sorry.
we see. Now we see.
I keep forgetting that I keep forgetting that there's a certain order of operations I have to do to make this work, and I keep reversing the order of operations. So this P inverse is multiplicative inverse, right? So for example, 5 inverse is the number which, when you multiply it by 5, you get 1, right? So you can think of it like this.
You mean 1, but we talk congruence, 1 in general?
Right, yeah. So this is what 1/5 means in Q, in the rationals, like in the normal arithmetic. But you can also talk about multiplicative inverse mod some number. For example, I can say that 2 inverse is congruent to 3 mod 5, because this is true if and only if 2 times 3 is congruent to 1 mod 5. It's the number which, when you multiply it by 2, you get 1 in this modular universe, right? So this is what the modular inverse means. Now let's look at the inverse. Is everyone okay with that? Cool. So
can we just, David, to make our problem simpler, we multiply it by p, all our relation, and we get.
Yeah, that's
is
the
not
key
confusing.
idea. That's the key idea. So the key idea is that if you multiply both sides by p, you get a quadratic. At least quadratic in this modular 143 universe. So if I take this and multiply it by p, you get p squared plus 1 is congruent to 25p mod 143. And so therefore this becomes p squared minus 25p plus 1 is congruent to 0 mod 143. Now it turns out I purposely made the number so that this quadratic is actually pretty easy to solve.
Yeah, because if you make them 11 and 13, they become very good complete squares, right?
Yeah. You can do that. The way that I managed, the way that I concocted these numbers, and I'll talk more about how I came up with this problem in a little bit, is to note that this thing right here, yeah, basically congruent squares. Not congruent squares, but 1 is congruent to 144.
Yeah.
And so this becomes a quadratic that we can actually factor.
Nice.
P minus 9 times P minus 16 is congruent to 0 mod 143. So that means that the solutions are p is equal to 9 and p is equal to 16, right?
Wait.
Wait a sec. What's wrong? What's going on here?
They're
Why
not
did I
prime.
why did I phrase that as a question instead of a statement?
Because you're not very confident in yourself.
That's a personal problem that I struggle with every day. But more importantly, why can't we just say why can't we just say, oh, these two factors multiply to 0, therefore one of them has to be 0?
Well, 11 times 13 is 0.
Yeah. In very technical jargon, the ring of integers mod 143 doesn't satisfy the zero product property. It's not even in a so-called integral domain. But in less fancy language, I can take two non-zero things, namely 11 and 13, and multiply them together and get something that's in 0 mod 143. So I can't use the zero product property here. But as we've alluded to, this sort of we are allowed to use the zero product property when your modulus is a prime, because of I think it's Euclid's lemma. P divides AB implies P divides A or P divides B. I think we talked about this last week actually.
You're a very
So-
good historian.
I taught a course in number theory, so I had to memorize. I felt compelled to memorize this. So if we
So
look
wait,
at this,
David, in
yeah.
simple words, we're looking for a prime p such that p minus 9 times p minus 16 is divisible by 11 and is divisible by 13, right?
Yes.
And you
Yes. So that
split it
means there are
into
4
two
cases.
parts, right?
There are 4 cases.
Mhm.
So the first case is, or rather, let me say this. Let me say that P is congruent to 9 and 16 mod 143 are solutions, but they're not the only ones, right? How can we get another solution? Well, we can make P is minus 9 congruent to 0 mod 11, and P minus 16 congruent to 0 mod 13, or we can make P minus 9 congruent to 0 mod 13 and P minus 16 congruent to 0 mod 11. Right? These are the 2 possible options that are not
This
just
is what you have.
yes, in addition to what I have. And I've already worked these out. So these are, let me just make sure. Yeah, this one gives you P is congruent to 42 mod 143. And this one gives you P is congruent to 126 mod 143. Right? Just you can check this on your own. I don't want to actually do the computation. If you're interested in learning how to do this sort of computation, read up on the so-called Chinese remainder theorem. Or it might not necessarily tell you exactly how to do it, but it gives you the basic idea as to why we should expect these different congruences to play out in the right ways. So what do we get here? We're almost done. So we know that this system is solved if and only if P is congruent to one of 9, 16, 42, and 126 mod 143. And now we just need to find the smallest prime that satisfies these.
Yeah, not prime. So plus 143?
Yeah, none of these are prime, which is kind of sad, but it's okay, because that all this means is we just have to add 143 and to all of them. So the next set of numbers that works is 152, 159, 185, and 269. Okay, so these guys aren't prime. Is 152 prime?
Well, no.
Good. Okay, I was testing you. Is 159 prime?
Mod 3.
Yeah, mod 3. Sum of digits is divisible by 3, so you can check that pretty easily. Is 185 prime?
You wish.
Oh, no.
Nope. Good. 269. Is 269 prime?
Looks like it.
Yeah, you have to check divisibility by 11, 13. That's it, because 17 squared is greater than 269. So all you have to do is check 11 and 13, and they both fail. So 269 is prime. Hence is our answer.
So being prime is not really a relevant part to this problem, right?
Correct. being prime is just a means for me to try to make sure that you actually solve the congruence. It's like basically a way for, if I remember correctly, it was a way for me to basically encode the answer in a weird way. So let me talk about how I came up with this problem. I made this problem during summer vacation, right before I was going to be a freshman in college. So actually, the story of this problem is that this problem took me 2 days to write. The first day I wrote, I was thinking about what would happen if you had a system of congruences, but your congruences were in different moduluses. And I was thinking of things like that, and in the end I came up with this problem, which I don't think I've ever shown to the public. Determine the number of ordered pairs A, B of positive integers, each between 1 and 63, inclusive, such that AB is congruent to 1 mod 7 and A plus B is congruent to 1 mod 9. So this is basically looking at like you have your left congruence, which is mod 7, and you have your right congruence, which is mod 9. So I remember I was in the ocean because we went to the beach for vacation, and I was trying to solve this problem in my head. I know, I'm a weird person. It's okay. I get that all the time. And in the end, I came up with this ridiculously complicated solution, and I was like, wow, this is a really hard problem. Then I later realized that this just dies to Chinese remainder theorem, and that sort of deflated a lot of what I had in mind. Here's why it deflates the Chinese remainder. Here's why it dies to Chinese remainder theorem. Let's say you're given an A. Say you're given A mod 63. Assume that so if you're given A mod 163, then you basically know two things. You know the value of A mod 7 and you know the value of A mod 9. But the first equation, assuming that A is not 0 mod 7, gives you B mod 7, and the second equation gives you B mod 9. So if you combine those two things together, you get B mod 63 uniquely. So as long as A is not divisible by 7, you get a unique solution. Therefore, the answer is 54, if I remember correctly. 54? Yeah, it's 54.
Mm-hmm.
So this is kind of nice, but compared to the ridiculousness of the solution I found while I was surfing in the waves, I was very disappointed. So I put the problem down and tried to do something else with it. The next morning, when I was also walking to the beach, I know, don't judge. I realized that maybe you could do something interesting when the modulus is, like, you have this system of congruences, but you could still do something interesting when the moduli are the same. So let's say AB is congruent to 1 mod 7 and A plus B is congruent to 1 mod 7. If you take those two things together and combine them into one equation, you get A plus E inverse is congruent to 1 mod 7. And that's the system you have to solve. And you realize that, okay, if you multiply by A, you get a quadratic, and then it's just a matter of making sure that the numbers work out in such a way that you try not to hack it. In particular, I chose these numbers for a few reasons. I chose 143 and 25 so that you could take the quadratic and factor it easily. I was specifically looking at quadratics of this form, where if you take 1 plus something, it factors into something really nice. And it just so happens that perfect squares do the trick really easily here. I also chose these numbers in particular because of the fact that the answer that we came up with, 269, came from 126. And 126, in order to get 126, you need to know how the Chinese remainder theorem works. So you can't if you just assume that P is congruent to 9 or 16 mod 143, you're going to get the wrong answer if you do this. So those are like two big reasons why I happened to choose the numbers that I did.
Mm-hmm. I can definitely agree with David's sentiment. I can't tell you the number of times I've created a problem with a beautiful, very extravagant, beautiful, long, windy solution, and it just turns out it's trivial if you just look at one small thing. So it's really disappointing as a problem writer because you spend a day or two making a problem that's beautiful, and no one's gonna ever solve it because you had to contrive a bunch of you contrive it from the solution instead of from the problem. So you have this elegant solution that no one's ever gonna find, and then you realize it's just a dumb problem. So that happens a lot. Also, the beach story.
Oh no.
I spent this entire last summer in Singapore, and that's also when I wrote most of my problems for this year's HMT. And then I think one weekend I was in Krabi. I was just like in the like we were just like on a boat, like a bunch of us, and I spent my day at like many different beaches, and I spent the entire day creating like this year's algebra number 6. It was really sad because it was like so amazing outside, but it gave me something to do because being at beaches is eventually like pretty boring. So I understand.
I agree.
But
I
yeah.
also generally find it's also kind of funny how so many of my problem stories basically end up boiling down to I procrastinate on doing things I actually should have done to work on math problems. I'm not sure if this is a good thing or not.
Yeah.
Yeah.
Okay, I don't think we have the time to do the fourth one, but so I want to go back to what David did earlier. Can you still share us the board?
Yep. I just want to share my face.
Okay.
Yep.
Okay. You know, I understand that this is the very cool step, right? Because you can factor to suit this problem. But I don't want our audience kind of like being scared into, oh, I must know this little trick to do this.
Sure.
Because to me, I still think if you do p squared minus 25p plus 1, mod 11 and mod 13 are more natural approaches. So let's say, for example, you do get a p squared minus 25p plus what? Can you write it down?
Yeah, writing not in tablet form is going to be a little tricky, but I can make that work.
Yeah, I just want to give students a general idea about what to do in the sense they didn't see this adding 143 to factor. For example, if you let's just stop at here. Okay, we can just go with which one? We can go with the 13 one. 13 one, we can write the next step as p squared plus p plus 1 congruent to 13, right? Because we add 26p. Right? And at this point, I think it's still more kind of like a brute force way or bashy way or whatever, or more systematic way, is you still, when you solve equations, you still want to solve quadratics, like you're solving quadratic equation. So that means what? You basically have 4p squared plus 4p plus 4 congruent to 0 mod 13. So even though I'm doing a much more complicated way, at least I want to let students know this is more or less still workable. And then you got 2p 1 squared congruent to 10, right?
I'm going to go with -3.
A -3, yeah. At that time, you still can figure out what are the possible values for what? 2p plus 1. Because 3 must be a square, a quadratic residual, right?
Yes.
You hope. And then from there on, you can
-3.
find all the solutions kind of like more systematically, right? Right? If you didn't see it. So this is still doable, right?
Yeah.
So -3 is a 36, right?
Mm-hmm.
Yeah.
Yes.
-3 is 36, yeah. So you have you know it's plus minus 6, right? You can run through the residual system very quickly to find out which two are the ones, right?
David, let's write 36 and then you can show that it's a difference of squares. So,
So 2p, I'm going to use a different color because there's the green right there. I'm very picky with my colors. 2p plus 1 squared is congruent to 6 squared mod 13. So that means that 2p minus 5 times 2p plus 7 is congruent to 0 mod 13. And now, because 13 is a prime, you can use zero product property elements.
Yeah, and if you want to review what's the inverse, now you can find the inverse of 2 and to make it work, right? So for the students who are still not familiar with this, we can write down 2p congruent to 5 equal to 13. And then let's see what's the inverse. What's the 2 to the -1 mod 13?
Well, what number do you multiply 2 by to get something that's 1 mod 13?
Right. -6, right? Or 7, yeah, whatever.
I'm going to do 7.
Yeah, yours.
So if I multiply both sides of the equation by 7, or both sides of this congruence by 7, this left-hand side reduces to just p, And the right-hand side reduces to 35, which is going to mean -4 or 9, which is very convenient because
which
we
is
got
our original one, right?
And this technique of completing the square is actually super powerful because it tells you, for example, when you can have what primes will divide numbers of the form n squared plus n plus 1. You can repeat this trick. I don't remember the exact criterion. It might be p congruent to 2 mod 3, but I'm not so certain about that. No, wait. P congruent to 1 mod 3. P congruent to 1 mod 3.
Cyclotomic polynomial.
Yeah.
Yep, cyclotomic polynomials. You're right.
I just want to say to the audience, one day you guys will study not only, okay, when we study Chinese remainder theorem, we are solving linear equations, right? System of linear equations, modulo different primes or numbers. And here we have another step up. We study linear quadratic equations. So when you study quadratic residues or something similar, think of it as something simple. It is related to the common algebra you study in school. Completing the square, same methods work nicely.
So this is really a cool problem, involving two very good things about number theory, right? Well, first of all, you should understand the inverse. Then you understand how to solve quadratic, and then you also how to understand how to solve linear systems. It's quite difficult, right?
What it's worth, I actually I did not know the whole multiplying by p trick when I first came across this, so I derived it by myself. I derived it by myself, which I thought was I was pretty happy about that.
Yeah. Okay, what time is it? Is about time to go or what?
8:57.
8:57. Yeah. So, okay. We can give them the question, let them think about it, and we can start next week.
Oh, let's do a teaser.
Teaser. Okay.
I'm gonna stop my share.
Yeah. So next week we are going to discuss this problem. We will not tell who is the author, where it was proposed. I don't know actually. But the problem is like this. James, can you please read it for us?
Yeah. There are 4 integers a, b, c, and d, with a is less than or equal to b, less than or equal to c, less than or equal to d. To satisfy the property that the product of any two of them is equal to the sum of the other two. Given that the 4 numbers are not all equal, determine the 4 tuple a, b, c, d.
Don't think about that while you are walking. This is one advice to our students. Safety is more important,
Well, where are they gonna walk?
I don't know. Because you guys keep
to the beach like David
you can
does.
go to the beach, think about
If you go to the beach, this is a bad idea.
Yeah, when you are
Hey,
at
you
the
can
beach,
still
make
take
sure you
walks.
are safe first. Okay?
Actually,
Taking walks is healthy.
I
Do
think
it.
Florida actually opened their beaches, so maybe.
They did, yeah.
So maybe you can go down to Florida.
So taking walks is healthy. Do it.
Yeah, but make sure when you walk, be a little bit careful. I know you are thinking about some math questions or whatever, but you really have to be careful. Okay, guys.
Yes.
I learned this from my own experience. Sometimes I hit things, and sometimes if things hit you, it's trouble.